45 years ago, on a sultry summer evening in Delaware, Ohio, something remarkable happened. From the direction of the Sagittarius constellation, an intense and continuous narrow-band radio wave bounced off a 30-meter tall flat reflector tilted towards the sky. It then bounced off another parabolic reflector, funneling it towards one of two detection horns that received and amplified the signal. Within the nearby control room, there were no scientists or engineers to watch the moment like in a Hollywood film. Instead, within that dark and lonely space, the only sound was that of a busy line printer and an IBM 1130 computer, diligently whirring and chirping away into the night. The computer printout fell into the tray, folding under the weight of the subsequent pages, but upon that page, the irrefutable evidence of the radio signal had been immortalized. Sometime later, a technician dropped off the printouts at the home of volunteer Jerry Eman, who had agreed to look through them for anything interesting. Scouring through the pages, Eman would carefully scan through the various numbers with his red pen. Most of the time, the numbers were small integers representing the signal-to-noise ratio the detectors received. Numbers greater than 9 had to be represented as letters, A for 10, B for 11, and so on. And so, when Eman stumbled across the sequence 6EQUJ5, he realized that he was looking at the highest signal-to-noise event he'd ever seen. Instinctively, he circled the sequence and wrote the now historic scribble. Wow. That happened in 1977, and despite 4.5 decades that have passed since, the WOW signal remains the most compelling candidate for an alien radio transmission we have ever received. I've long been fascinated with the WOW signal. Like an irresistible itch, I've often found myself dwelling on it at night in quiet moments, wondering, what was it? Who sent it? And what else could be out there? Radio signals are detected from the sky all the time, to such an extent that there's an entire field of astronomy dedicated to mapping the sky in the radio. But the WOW signal found by the Big Ear Observatory stands out as being incredibly exciting because of 4 observational facts. Number 1, its high signal to noise. 2, its particular frequency. 3, its narrowband signature. And 4, its apparently continuous nature. For fact 1, the high signal to noise is crucial because it removes any doubt that this could be some kind of random statistical fluctuation. The peak intensity of the WOW signal was 30 times higher than the ambient background. So that means that the probability of a random fluctuation doing this was 1 in 10 to the power of 196. That's an astronomically tiny number. The Big Ear Observatory could run for 1 trillion years and never expect to see a fluctuation like that. Yet more, the moments just before and after the peak also show exceptionally high signal-to-noise values, so there's no way that we can legitimately ignore this as some kind of statistical fluke. For fact 2, the signal frequency was almost precisely equal to the famous frequency of 1420 MHz, also known as the hydrogen line. This is a special channel, long hypothesized to be a likely wavelength that aliens might use to attempt to communicate with us because of 2 major reasons. First, the cosmos is naturally quietest at this part of the spectrum, so there's less noise to interfere with the communications. And second, the hydrogen line corresponds to the emission caused by the most basic electronic transition within the simplest atom in the universe. Anyone in the cosmos who understands quantum physics should know about this special frequency, and so it serves as a Schelling point, a rallying point in frequency space. Now, it should be noted that the frequency actually wasn't quite exactly equal to the hydrogen line, but instead was 50 kHz above it. However, this slight difference is consistent with the variation expected due to the Doppler shift of a transmitter that is moving towards the Earth at a modest speed of order of 10 km per second, which is a fairly typical velocity for nearby stars. For fact number 3, we turn to the narrowband nature of the WOW signal. But how do we know this? Well, the Big Ear Observatory had 50 detector channels, each one with a bandwidth of 10 kHz. The WOW signal was only recorded in one channel, channel number 2 of the 50 possibilities, which means that its power is limited to within a 10 kHz window, or even possibly much smaller. So, given the frequency of 1420 MHz, that means that the bandwidth divided by the frequency is less than 7 parts per million, incredibly narrow. Now, in nature, we simply don't know of any radio sources that do this. For example, the Crab pulsar is often referred to as a natural narrowband radio source, but there, the spectral ratio is 1 part in 10. Even if we turn to the recently discovered and mysterious fast radio bursts, you still only get down to 1 part in 20. The truth is that short of an artificial transmitter, we really don't know how such a narrowband signal could ever be produced. Of the 4 facts, this is perhaps the most important. Finally, turning to fact 4, the signal appeared to be continuous during the 72 seconds that it was observed for. Now, when you actually turn the numbers and letters into a graph, you see a bell curve like this, not a flat, continuous line. But here's the thing, because of the Earth's rotation, the observatory is sweeping over the field during this time, meaning that in fact, the bell-like curve is exactly what you'd expect for a continuous source. Fact number 4 is important because most satellites reside in a low Earth orbit where they would pass through the WOW field much faster than the 72 seconds that the signal was observed for. For example, the International Space Station would pass through the WOW field in less than a second. So you'd only get one single high digit, not the persistent sequence of 6 that was observed. These 4 properties are essentially exactly what you'd expect from an alien transmitter, and likely a very high-powered one. Now, it has to be said that a human-made orbiting satellite cannot be excluded, but they would need to be on a wide orbit beyond the geosynchronous orbital altitude to yield a sufficiently slow speed, which was rather unusual in 1977. Yet more, that signal will be utilizing a protected frequency, since the hydrogen line is internationally agreed to be a protected channel. Spy satellites also don't make a lot of sense here because, after all, radio astronomers across the world are very closely monitoring that wavelength, so it really wouldn't be very secretive to be using it. Emission from a comet has also been previously suggested and made the news a few years back, but it has largely been rejected by the community since they do not emit strongly enough at this frequency, nor were the sighted comets even in the beam at the correct time. So in summary, we have these 4 observational facts that together look quite promising for the validity of the WOW signal. But on the other hand, we also have 4 holes in our knowledge that frustrate us and ultimately leave the door open to skepticism about the WOW signal. So let's go through these 4. Number 1. We don't know if the signal was modulated or not. 2. We don't know where it even came from. 3. The signal was strangely only detected in one horn. And 4. We've never seen it repeat, ever. Points 1 and 2 are really just a product of the observatory's limitations. The detector was not sensitive enough to detect AM or FM modulation, so there could very well have been a message embedded within the WOW signal that we just never saw. Obviously, if we had seen something like that, it would have removed any doubt that this was truly from an artificial transmitter. Point 2. The unknown location surprises many. Surely a telescope knows what star it's looking at, right? Well, Big Ear has 2 big issues here. First, each horn spans a fairly wide field of view, about 1 by 20 arc minutes on the sky. Second, we don't actually know which horn detected the signal in the first place. That was never recorded. Alberto Caballero recently investigated this issue, showing here the large region of space where the source could have come from. There's thousands of stars in here, but Caballero tries to narrow this down to 60 nearby sun-like stars as the best candidate. But frankly, we have no idea whether the source was indeed a sun-like star, or even from a star at all. Point 3 is a weird one.
the two detect horns actually sweep over the same patch of the sky, but their physical separation means that they see that patch 3 minutes apart in time. Now, because we actually don't know which of the two horns detected WOW, that means there are two possible scenarios.
In scenario A, the first horn detected the continuous radio emission from the WOW field, but the signal then switched off in the 3 minutes between the horns. Or in scenario B, the signal was not present in the first horn, but then it switched on in the 3 minutes between the two horns. Either way though, it seems rather fortuitous that the big ear just happened to be looking at the right moment to catch the switchover, unless WOW is just constantly switching on and off.
And then to top it all off, we have point number 4, which is perhaps the most frustrating part of this whole story. Because despite many efforts to re-observe the WOW field, there have been no detections of a recurrence of that signal. With just one detection, the signal is tantalizing, but not definitive. So, where does that leave us?
Well, definitive proof that the signal was indeed astrophysical and not some terrestrial interference or space debris demands a repeat detection. But on the other hand, a lack of repetition also does not comprise definitive proof that it was spurious either. So we're left in no man's land.
Or are we? As subscribers of our channel will know by now, my approach to science often takes a rigorous statistical approach to such problems. And so one might ask, could the absence of any recurrence of that WOW signal be used to exclude it as an astrophysical source and then just move on with our lives? And so this is where our new research paper comes in, where we take a deep statistical dive into the WOW signal and aim to squeeze that data as hard as we can.
Many of you will know that we've discussed the WOW signal before on this channel in our Black Swans video. There, I discussed a different Cool Worlds research paper where I developed an analytic model for dealing with one-off events. The model works very well when you have a single observatory with constant settings, but WOW has been pursued now from many different observatories. Yet more, in that video, we saw how the unknown duration of the WOW signal causes a real headache, and different assumptions lead to very different answers about its likelihood of recurring in the future.
And so after that last video, I wasn't satisfied. I wanted to go back and do the WOW signal justice to fix these issues and complete a final analysis. I wanted to know, I needed to know, could the WOW signal still be a viable alien transmission even after all of those null results?
Whilst making that video, I started corresponding with Robert Gray, who literally wrote the book about the WOW signal. Perhaps more than anyone else, Gray has pursued WOW with a feverish curiosity, visiting the original site, interviewing the team, and studying the technical diagrams of the observatory. He even set up a 12-foot radio telescope in his backyard to continuously monitor WOW from home. Remarkably, even though he was not trained as an astronomer, he was awarded telescope time on the Very Large Array in New Mexico to look for the WOW, the first amateur astronomer to ever use the facility. So after the video was posted, we continued to correspond about the WOW signal and started working on a new, improved analysis.
So what is new here? What is the big idea? The basic premise of our approach is to create a responsive emulator of the Big Ear Observatory and indeed the other observatories that observed the WOW field.
Back in 1985, Gray had visited Ohio State University, who operated the Big Ear, and managed to reconstruct the exact dates of each and every time Big Ear looked at the WOW field. Even though WOW was only seen once, Big Ear actually observed that field on 122 unique days, spanning August 1977 to March 1984. However, only 90 of these were actually useful observations due to various issues at the site. We also know that Big Ear has this peculiar observing mode where two horns pass over the same patch of the sky each day, separated by 3 minutes, and each one observing for just 72 seconds. So equipped with this information, can we now simulate a hypothetical alien transmission from the WOW field and ask in how many of those 180 observations would we expect to detect it?
Now, this is where the fun begins, because with our emulator, we can change the properties of our hypothetical alien transmissions and see how would it affect the observations that Big Ear would get. So, for example, if the signal repeated like clockwork once every hour and stayed on for about 10 minutes, then we would expect about 30 detections. However, if the signal repeats, say, once every millennia instead, then we would get 0 detections.
In this way, we have a Big Ear sandbox, if you will, where we can play God with different alien transmissions and see what Big Ear would report each time. Now, there's a certain degree of randomness here because apart from the alien signal's periodicity and duration, it also has some arbitrary start time, which we simply randomize in the simulations. So for any given alien signal, we actually generate thousands of different realizations of it and then average them together at the end.
So the real point of all of this is that we can now ask the question, what kind of alien radio transmission do we have to generate such that it matches the properties that Big Ear saw for the WOW signal? In other words, out of 180 attempts, how do we get just one success? Now, to make progress though, we have to choose between one of 2 types of alien signal.
In case 1, it repeats like clockwork on a regular constant schedule. So, for example, this could be an alien transmitter that resides on a rotating exoplanet. Or in case 2, it repeats randomly. Perhaps this might be unintentional leakage from an advanced civilization that sporadically points towards the Earth. Perhaps even it could be an automated beacon that deliberately follows a random schedule, since it turns out this would actually minimize the chance of a signal being missed by a receiver on a planet with a fixed rotation rate, like the Earth.
Now, some of you might be thinking to yourself, hold on, what about if the WOW signal was a one-off event, not repeating at all? But actually, technically, a one-off event is still a repeating event, just where the repeat time equals infinity. And so mathematically, we don't have to change anything here. It is fully encoded within our framework.
The first case of a periodic signal has been studied extensively already, including by Gray himself. The summary of this is that any periodicity below 14 hours is completely excluded, and even beyond that looks very unlikely. So if we assume that alien transmitters have to be periodic, well, there's really not much chance of WOW being what we might have hoped it was. In this vein, the best way to save WOW is to assume that it's not periodic, but rather it follows some random schedule.
But even randomness can be characterized statistically. If we assume that the average number of pings per unit time is unchanging, then that means that the events must follow the well-known Poisson distribution. What this essentially says is that yes, the events are being generated by some unknown random generator, but the properties of that random generator are themselves not changing in time. So now the WOW signal is characterized by just 2 parameters: the duration of the pulses, let's call that t, and the average rate of pulses per unit time, let's call that lambda. Equipped with our Big Ear emulator and our random signal generator, we are now finally ready to figure out what are the properties of the WOW signal. To do this, we essentially create a dense 2D grid of possible duration, t values on the x-axis, and lambda values up on the y-axis, and ask in each one of these simulations, how often do we get a WOW-like signal? In other words, just one success from 180 observations.
You can see here the color-coded map that we recover, where the white region there leads to the highest odds. In that region, the peak probability is in fact 32.3%, almost a third. So that means that the fact that we saw just one WOW signal from the years of Big Ear observations is actually not that weird. It's a 1 in 3 outcome if the WOW signal has a T and lambda in that region.
This is why statistics is so important, because let's compare that to our intuition, or in fact the intuition of Jerry Ehman, who, remember, was the person who first discovered WOW back in 1977.
In a 1994 interview, Jerry said, "We should have seen it again when we looked for it 50 times. But here, we find that it's actually not particularly unusual that Big Ear never saw it again, even after 90 observing days, so long as the WOW signal has the right T and lambda."
But hold on. So far, we've only used the original Big Ear observatory data, but remember, in the years that followed, other observatories have pursued the field and also come up empty-handed. Surely, if we add in this extra data, it will finally kill the WOW signal. Well, using our emulator, we can easily fold in this additional data and see what we get. Of the various follow-up efforts of the WOW field, 3 really dominate, and we'll focus on those here. In 1994, Robert Gray used the 26-meter Harvard-Smithsonian Radio Telescope for a total of 8 hours on target. Then, in 2002, Gray was at it again, but now using the University of Tasmania's 26-meter radio telescope, on target for 84 hours in total. And finally, in 2020, Harpadow joined the hunt and used the Allen Telescope Array to collect more than 100 hours on the field. So that means there's been more than 184 hours of accumulated observations since the original Big Ear data, and all of this new data has even higher sensitivity than the original Big Ear Observatory did. So look, I get it. It's easy to see why a director in an observatory would just shoot down any proposition to keep going at this point. But critically, is that a rigorously justified position? Using our emulator, this tranche of new observations definitely reduces the overall probability of a random WOW signal matching all of the existing observations. Whereas before our peak probability was 32.3%, about a third, the best matching T and lambda now slide down to a probability of 1.8%, so about 1 in 50. Now 1 in 50 is undeniably improbable, but it's also hardly implausible. It corresponds to 2.4 sigma in statistical parlance, but in science we would only normally consider a hypothesis rejected if it crossed the 3 sigma threshold. So that means that we would have to change this 1.8% number to 0.3% to finally reject WOW. In our paper, we can use the emulator to actually predict how much more data is necessary to get to that point. And the answer? Around 1,500 hours of additional observing time would be necessary, or 62 days of accumulated observations. That might seem daunting, but it could be achieved in a single year with aggressive scheduling. And the payoff would be a conclusive answer at last. Either we see WOW repeat and know it's the real deal, a frankly earth-shattering result, or we see nothing and can finally exclude it as an astrophysical source to high statistical probability. Now, one thing I haven't revealed yet are what are the most likely properties of the WOW signal. I've told you those most likely properties have a 1 in 50 chance of occurring, but what are the associated duration, T, and mean repeat rate, lambda, that correspond to that most likely solution? Coupling our emulator to an inference framework, we can constrain that the duration of the signal is between 2 minutes and 37 hours to 95% confidence. And as for the mean repeat rate, that comes in between about once every other month to 12 times per month, again to 95% confidence. Very slow repeat times, those less than once per year, are strongly disfavored by the existing data, as they almost always lead to 0 total detections, rather than the 1 WOW signal that was observed. So in conclusion, WOW is still alive, just about. It may be a real repeating signal, a scenario with a probability of 1 in 50. Or it may be bogus after all. Something that we could conclusively state if we collected just 2 months extra of new data. Here, we've tried to push the statistics as far as we can, but there's only so much we can model. Perhaps our assumption that the mean repeat rate doesn't evolve is wrong. Maybe someone is behind the controls of that transmitter who has substantially modified the mean repeat rate over the last 45 years. Who knows why, but it's not impossible. In science, though, we try to proceed with the simplest model possible that's justified by the data, a philosophy that harkens back to William Ockham. And in this case, with a single datum, I don't think we can usefully propose a more elaborate model in the absence of additional data. But even so, our analysis shows that hope remains. WOW could be still out there, just waiting for me or for you to go to the telescope and hear it again. To close, I want to share one last thing with you. Robert Gray was the co-author with me on this new research paper, but during the writing up of this work, he tragically passed away in December last year.
I didn't know Robert personally, but professionally, he was a true gentleman with whom my interactions were always warm and spilling over with enthusiasm for the WOW signal. And that's clear from his life. A data analyst by day who trained himself to become the world's preeminent expert on the WOW signal.
I strongly recommend you pick up this book. This is The Elusive WOW by Robert Gray. It is the definitive book on the topic and a great read. Look, despite the tragedy of Robert's passing, I personally have some solace that this final project he wrote on the WOW signal led to the result that there is still some hope of WOW recurring. Not a lot of hope, but a little. And maybe enough that someone out there, perhaps watching this right now, might pick this up and one day resolve the WOW mystery. I'm glad that I got to help Robert with that. So, until next time, stay thoughtful and stay curious.
Why care about life elsewhere? That's a good question. Life here is a riot of different forms, colors, sizes, noises, environments, behaviors. And I think that people probably have an innate interest in whether something like that happened elsewhere. And the only way to settle that question, of course, is to go look.